Hey guys, Mr. Midas is here, and the shade is kind of off here. I'll get there where I am. Hey, this is 3-1 for BC Calculus. For Calculus Extended, so I'm going to talk about concavity and points of inflection, we call the second derivative test. So let's start, this is going to be in 2 videos, by the way. So let's go ahead and start doing this guy right here. Oh, come on, man. Shrink me. Shrink me. There we go. All right, so let's talk about concavity. So a graph is called concave upward if it goes like this, kind of like a bowl. All right, that's concave upward. Now, what happens when it's concave upward? Our tangent lines are below the graph, and they're not only below the graph, but as we continue going left to right, they increase in slope. So if they increase in slope, it would mean that the tangent lines are increasing in slope, meaning that the second derivative, because it's the rate of increase of the tangent lines, the second derivative is greater than or equal to 0, so that's positive. For concave downward graphs, concave down, the tangent lines are on top, and going from left to right, they're actually decreasing. The slope is decreasing, so if the slope is decreasing, then the rate of change of the slope is getting smaller, meaning that the derivative, which is the second derivative, is negative. So second derivative being negative will tell us that the graph is concave downward. Now, just an easy way to remember what is what, whether it's going upward or downward. A smiley face is positive. That is concave upward. Smiley face. Frown, sad face is concave downward because we're feeling down. And it has negative. It's negative. We feel down when things are negative. We're sad face, right? Boo. So a second derivative is negative, meaning it's concave down. So how do we know where a graph changes from being concave down and concave up, or concave up to concave down? Well, we know that things change concavity at what we call the point of inflection. At the point of inflection, the graph does have a tangent line, and the graph changes its concavity. So, on the graph of x cubed, as I have here shown, the point 0, 0 is a point of inflection because it changes from concave down to concave up. There's the point of inflection right there. All right, so let's take a look at an example. All right, we have this graph here, and we're going to look at some examples, look at some things about concavity. So on which intervals here is the graph concave upward? So we're looking for concave up, which is a smiley face, right? So where is a smiley face? Well, it's concave up right there. Then it goes concave down, and then up again. And then this actually keeps going up, I think. Maybe this actually looks like a straight line. So I think this is straight. Then this is concave up, and then concave down. So concave up looks like it's going to go from -2 to -1, and then again from 1 to 3, and then again from 4 to 5. Now, where is it concave down? I'll use red, concave down. Boo, concave down. This again looks straight, so that's linear. Linearity doesn't have any concavity, right? It's not curved, so it can't be concave up or concave down. So concave downward is going to be from -1 to +1, and from 5 to 6. All right. On which intervals does the graph have no concavity? So we just talked about that. It has no concavity from 3 to 4. So from 3 to 4, there's no concavity. And oh, you know what? There's a solid line here. We missed that guy from 6 to 7. What are the points of inflection? Well, the points of inflection are going to be where it changes from concave up to concave down. Now, there needs to be a tangent line there at a point of inflection. So if this isn't differentiable, it can't have a point of inflection. So notice here, this is a sharp turn. Oops, let's use a different color there so we can see this guy. Let's use purple. Okay. So right here, there's a sharp turn. right? So the sharp turn makes it not differentiable, so that's not an inflection point. Right here, this is a good inflection point. So we've got a point of inflection at 1, 1. Where's another good one? That doesn't really change concavity, so I don't like that one either. That's a sharp turn. Here we've got a nice smooth transition, so that's going to be 5, 1 is another point of inflection. All right, so points of inflection have to be, our graph has to be differentiable for that to be a point of inflection. All right, let's take a look at another example. Okay, we'll take a look here at some real examples of what we're going to be doing in terms of calculus. So analytically, which means algebra and calculus, to find concavity intervals and points of inflection, we got to use a second derivative, and then we'll use a number line to see if it's positive or negative. So it's similar to how we did increasing and decreasing intervals and extrema, only this time we're using the second derivative. So we're going to find the first derivative, boom, 4x cubed plus 3x squared minus 3x. Then we're going to find the second derivative, which is 12x squared plus 6x minus 3. We're going to set, oops, this was 6x. And then we're going to set this guy equal to 0. And we're going to solve for x here. Oops, x plus 1. And our possible points of inflection, our pips, possible points of inflection are going to be x equals 1/2 and x equals -1. Remember, they're possible points of inflection because we don't know if it actually changes concavity. What we're going to have to do here is use a number line, and we're going to check our possible points of inflection, -1 and 1/2. And we're going to check and plug in numbers and see what our second derivative is. So I'm going to try 0 here. If I put 0 in my second derivative, I'm going to get a negative. If I put like -5 in here, I'm going to get a positive. If I put a bigger number than 1/2, I'm going to get a positive. So what does this tell us? This tells us that this graph, the graph of f, is concave up for the interval from -infinity to -1, right? All these guys right here concave up. Over here is concave up. And so also 1/2 to infinity. It's concave down. In between there, -1 to 1/2. And our inflection points, well, we know that -1 is our x value, so I'm going to plug -1 back in for my f right here, and I'm going to get my y value, which is -2. And then I'm also going to do that for 1/2. So I plug 1/2 in here for f, and I'm going to get 7/16 when all the math is said and done. All right. All right. Let's take one more example for this video, and then I'll finish it up on the next video. So if f of x is this guy and second derivative is this guy, list the intervals for which the graph is concave upward, downward, and list the points of inflection. So here's the good news. I don't need to take any derivatives for that because I already have them here. I already have the second derivative right here. This is what I wanted to work with anyway, right? So first thing that I should notice is that the domain is that x cannot be equal to plus or minus 2. So I can't have any inflection points or possible inflection points there. If I try to set this f prime of x double prime equal to 0, it won't equal 0 because if I set the top equal to 0, I can't solve that. So f double prime is never equal to 0. So I really don't have any inflection points, right? So there are no inflection points. But that does not mean that the graph can't change from negative it doesn't mean that I can't have different intervals of concavity, because I could, for instance, I could have something that goes like this, and then I could have something that goes like this, right? Well, that's concave up, concave down. So I still have to check for the concavity. And the way I check for concavity is I look at the vertical asymptotes. So I know that my vertical asymptotes are x equals 2, x equals negative 2. So my number line now is going to be at those vertical asymptotes. Negative 2, which what I'll do here is I'll put dash lines, and positive 2. And I'm looking at my f double prime here, right? So what I'm going to do is I'll pick a number in between here, 0. I'm going to plug it back into right here, my f double prime, and see what I get. That's going to give me a negative value. I'll put a number here on this side into my thing, and I'll get a positive value, and I'll put a one from here, and I'll get a positive value here. So I do have some different concavities for my graph. So I'm going to go ahead and discuss those. Concave up. It's going to be concave up from negative infinity to negative 2. And from 2 to infinity. It's going to be concave down from negative 2 to positive 2. And I have no inflection points. All right. All right, so there we go. We've got 2 examples of using the second derivative to find our inflection points and to determine when a graph is concave up and concave down. In the next video, I'll look at a few more examples. See you soon, guys.